Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. The course we are going to discuss today in this video is sizing of centrifugal compressor. This course will be presented in two-part series. Part 1, sizing of centrifugal compressor. Part 2, sizing tutorial on centrifugal compressor. The learning outcome of this course is to learn how to size a centrifugal compressor, to understand the importance of process parameters while sizing and developing the specifications. We will move to part 1 now, sizing of centrifugal compressors. Sizing of centrifugal compressors is a process engineering activity in the development of process design package for a new plant. Centrifugal compressors are widely used in oil gas industry, refineries, petrochemical plants and fertilizer plants. They are considered one of the critical and fundamental components of the process plant. Some specific applications in the industries include product gas compression in olefin plants, refrigeration gas compressor for chillers and for cryogenic olefin paraffin distillation column, overhead condensers, natural gas liquefaction and fractionation, syngas compression and recycle in ammonia plants, excess reactants recycle in petrochemical plants. The primary function of a centrifugal compressor is to take in certain mass of gas at some temperature and pressure and delivers the same mass at higher pressure and temperature. The centrifugal compressor has three sections: inlet section or suction nozzle, which accelerate and directs the gas to the impeller I. May also contain inducer and gate vanes. The second component is impeller, the most critical component in the compressor. It provides kinetic energy to the gas. The third component is diffuser, which converts part of the kinetic energy to pressure. Impellers are the only aerodynamic components in the compressor. They provide 100% of the kinetic energy that is added to the fluid and can contribute to about 70% of static pressure rise in the stage. Well-designed impeller can achieve efficiency as high as 96%. That means only 4% of the energy expended is lost. Losses in the stationary hardware reduce the overall stage efficiency from the baseline established by the impeller. The application range of centrifugal compressors: capacities ranging from 500 to 300,000 actual cubic feet per minute, which is equal to 850 to 510,000 actual meter cube per hour. Discharge pressure from 40 psi to 10,000 psi, which equals 2.5 bar absolute to 700 bar absolute. The maximum compression ratio is limited by the outlet temperature. The usual limit of temperature is 200 to 230 degrees centigrade. Why there is a limit on the temperature of the gas exiting the compressor discharge? The centrifugal compressors have a diaphragm between the impellers which tend to expand radially due to temperature rise of the compressed gas. Hence, for higher pressure ratios, to limit the temperature rise, multi-stage compressors with intercooling is used. Shown in the sketch is a two-stage centrifugal compressor. The gas with volume flow rate of Q1 enters the compressor suction at pressure P1 and temperature T1. The compressor delivers the gas at volume Q2 at pressure P2 and temperature T2. The pressure ratio is higher for a single stage to accomplish with the compressed gas temperature limitation, which is 230 degrees centigrade. Hence, the compression is accomplished in two stages. The stage 1, consisting of 3 impellers, raise the pressure of the gas to intermediate pressure P interstage and temperature T interstage. The gas is cooled in the intercooler, and the cooled gas at the same interstage pressure goes to the suction of the second stage. The second stage, also consisting of 3 impellers, raise the pressure of the gas to P2 and delivers at temperature T2 and volume Q2. Due to compression, the volume decreases, but the mass remains constant. The pressure ratio per stage with the temperature limitation is influenced by the value of K, which is a ratio of specific heats. As the value of K increases, the discharge temperature of the compressed gas increases. Hence, for gas with a higher K value, the pressure ratio without intercooling will be lower. The number of impellers in each stage depends on the extent of pressure rise that is required to be accomplished. A single impeller can develop only limited head rise per unit mass of gas. Designing and sizing. Many times, the doubt rises in the minds of the engineer: who designs the compressor and who sizes centrifugal compressor? The design involves determination of number of impeller stages, impeller diameter, blade axial width at the outlet of the impeller, rotational speed of the impeller, adiabatic or polytropic head, discharge temperature, gas horsepower and brake horsepower. The exact design of the compressor is made by the compressor manufacturer based on the actual mechanical design and operating conditions. However, many times the end user needs quick and reliable operating conditions estimates for process design and pre-engineering studies and economic evaluations. Cost of equipment is another important outcome of chemical process plant design. Quick estimate of compressor cost requires compressor horsepower requirement. This is obtained through sizing by the end user, that is company's process engineer. To size a compressor, one must specify the following: the flow rate of gas the compressor is required to deliver, the discharge pressure or pressure ratio compressor must develop to deliver the required flow rate, the composition of the gas, range of suction temperatures, that is minimum, normal and maximum value, range of suction pressure, again minimum, normal and maximum values. In addition, the end user may also specify the driver. The driver may be electric motor. In many situations, the driver may be steam turbine due to availability of steam in the plant. The head or pressure ratio required for the compressor is estimated from the compressor and connected compressor system layout. Now we will move on to the sizing parameters. How do we get them or how to estimate them? Capacity. Capacity is one of the most important parameters for the end user. Capacity or the flow rate can be specified as a range of mass flow rate, kg per hour or pounds per hour, or volumetric flow rate, cubic meter per hour or cubic feet per hour. The sizing data such as flow rate, gas properties are derived from the process flow diagram PFD of the process design package. Capacity at inlet conditions. What are the inlet conditions? Inlet pressure, minimum, maximum, inlet temperature, minimum, maximum, discharge pressure, minimum, maximum, discharge temperature, minimum, maximum, gas composition. Why to specify gas composition? Gas composition can change. Along with it, their physical and thermodynamic properties can also change. These properties include gas mixture molecular weight, gas mixture adiabatic constant at inlet and discharge, gas compressibility factor at inlet and discharge. These properties are estimated by process simulation. Gas composition analysis needs to be provided by the customer's process engineer as a part of the specification. Polytrochic efficiency is another important compressor design parameter which the end user's process engineer has to estimate and include in the specification. Driver type is also specified in the specification. For example, gas turbine, steam turbine, or motor driven. If the end user has sufficient high pressure steam available in the plant, then he may choose steam turbine drive. Before we move further with the sizing related discussion, I would like to mention about the impeller, though its design is within the purview of the compressor manufacturer. In general, the typical diameter of the impeller ranges from 150 to 1500 mm. Smaller the diameter, the better, because the size of the compressor will be smaller. But small diameter means higher rotational speed of the impeller. The maximum rotational speed is limited by the tip speed and tip speed Mach number. Another important parameter for the compressor sizing is pressure ratio. Pressure ratio is a ratio of discharge pressure to the suction pressure. It is also called the head. The head or pressure ratio required for the compressor is calculated from the compressor and connected compressor system layout. How to determine the pressure ratio or the compressor discharge pressure? The connected process system and compressor performance must be thoroughly evaluated as a single system to determine the pressure ratio or the discharge pressure required. The connected system may be simple to complex with many equipment depending on the application. Let us now see two examples of the compressor connected system to understand how the discharge pressure vary with the system. The resistance to flow experienced by the gas across the process equipment and piping as the gas flow through them results in substantial pressure drop and adds to the back pressure for the compressor. This back pressure is the discharge pressure of the compressor. Take a look at this figure. This is a typical process gas compressor loop. There are 8 process equipment in the gas loop. 1 dryer, 1 reactor, 3 number of distillation columns, 3 number of heat exchangers and associated piping and instrumentation. As the process gas flow through the equipment, it experiences pressure drop due to resistance. The pressure drop across each equipment is indicated alongside the respective equipment. So the total pressure drop in the system, which is delta PS, is a sum of all the pressure drops across the equipment and the piping and instrumentation system. This is shown here. So discharge pressure of the compressor P2 becomes P1 plus delta PS. So what is the pressure ratio now? The pressure ratio is P2 by P1, which equals to P1 by delta PS divided by P1. The pressure drop is a function of the capacity or flow rate through the process equipment. The pressure drop values are specified when preparing design specification for the process equipment. Design parameters such as tower diameters in the case of mass transfer equipment, tube and shell diameter, and number of passes in the case of heat exchangers are adjusted to achieve the pressure drop specification values. Hence, it is available and extracted from the process design document. You need the number of trays, height of packed beds, height of dry bed, etc. to estimate the pressure drop. Typical values of pressure drop across process equipment are listed here for reference. Tray columns 4 to 8 millibar per tray. Packed columns 1 to 1.5 millibar per meter height of packing. Dehydration dryers 50 to 100 millibar per meter height of bed. Heat exchangers tube side 0.5 bar, shell side 0.25 bar. Shown here is another compressor system. This figure shows a refrigeration chiller compressor used for ammonia synthesis by Haber-Bosch process. The compressor is used for condensing the refrigerant vapor generated from the chiller. In this system, the discharge pressure is not determined from the resistance to flow as in the previous example. The condenser pressure fixes the discharge pressure of the compressor. The pressure and temperature data shown here are only illustration purpose, not the actual industrial data. In the system example shown above, the discharge pressure is determined by the minimum cooling water temperature available for condensing the ammonia refrigerant. The normal cooling water temperature is in the range of 27 to 32 degrees centigrade depending on the plant location. At this cooling water temperature, the condensing temperature is 12.5 bar absolute. Hence, the compressor discharge pressure should be fixed at 13 bar absolute, including the pressure drop in the piping. The system resistance is much smaller or negligible compared to the total pressure in the case. Discharge temperature. Discharge temperature is another parameter the process engineer needs to estimate. The next parameter to be specified is the gas discharge temperature of the compressor. The compressor discharge temperature can be estimated using the polytropic compression equation as shown here. Gas horsepower GHP is a work done on the gas by the compressor. The next step in sizing is to estimate the power required for the compression. You have to select the expression for work done by the compressor. There are two expressions for the work done on the gas: adiabatic work done and polytropic work done. In the recent times, polytropic expressions are widely used for estimating the work done. The expression for polytropic work WP per unit mass of gas is given here. The work done on the gas per unit mass of gas is also called polytropic head HP. From polytropic head, you can proceed to estimate the horsepower required for the compressor. To do that, we need the estimated value of polytropic efficiency. Polytropic efficiency. Polytropic efficiency is yet another important parameter that needs to be estimated at this stage. Polytropic efficiency is widely used to describe the performance of centrifugal compressors. Polytropic efficiency is defined as the ratio of polytropic work to the total absorbed energy. So polytropic efficiency is another important sizing parameter. Centrifugal compressors operate at constant polytropic efficiency and polytropic head regardless of the gas compressed, provided there is no change in the inlet volumetric flow rate. Polytropic formulas are convenient when a given compressor's operating data for one gas must be used to predict its performance for gases with different Cp-Cv ratio and densities. Polytropic efficiency is a function of the gas throughput. Actual polytropic efficiency will change with speed, impeller design, compressor ratio, and other factors. Lastly, brake horsepower. Brake horsepower is estimated from mass of the gas and polytropic head and polytropic efficiency as per the formula given here. Now we have all the data to make the specification for the compressor. The data are listed in this table. This specification sheet is delivered to the compressor manufacturer for design. Actual design parameters and the operating conditions will determine the compressor performance characteristics. With the specification sheet in hand, you can go ahead and write the process duty point in terms of inlet flow and pressure ratio. The characteristics curve is a plot of polytropic head or pressure ratio versus capacity as shown in this figure. The shape of the curve is determined by the design parameters. Operating point is what the process requirement is, which you have specified. We will discuss about the compressor characteristics in detail in another session. Another important characteristic curve for centrifugal compressor is shaft power versus capacity. The figure shown here is an illustration of power versus capacity for a centrifugal compressor. Please subscribe to our channel and get updates on the upcoming videos by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation of part 1 of the two-part series on sizing of centrifugal compressor. Hope this presentation with narration and animation was useful. I welcome your comments, if any, about this course. Share with your friends and colleagues to reach out to large number of career-oriented professionals and students. Thank you for watching.